All right, so we're gonna move on to the next factor, okay, that affect the stability of the conjugate base. This one is electronegativity. All right, before we get into the details, so I want you to look at these four atoms, right? So we have carbon, nitrogen, oxygen, fluorine. They're on the same period. And you guys know from the periodic trend, atoms on the same period, the size is not that different. Okay, so size doesn't really matter for these four here. All right, but what different is, it's a big difference in electronegativity. We're gonna get into the detail in a bit. All right, so let's say if I have a hydrofluoric acid, water, ammonia, and methane, and they all act as an acid. All right, I'll tell you, so spoiler alert, fluoric acid is the strongest acid here, and methane is the worst. But how come though? So same thing, draw it out the conjugate base, and let's analyze which one is more stable. Okay, so first of all, size is not that different. All right, so negative charge on fluorine, on oxygen, on nitrogen, on carbon. Size of these atoms are not that different, so can't do size here. But what the big difference between these guys are, they have way different in electronegativity. All right, review real quick. So electronegativity is a measure of how strongly atoms attract electrons. Okay, and electronegative atom love to have electrons on it, negative charge on it. All right, so atom with high electronegativity tend to form negative ions. Fluorine love negative charge. Oxygen love negative charge. Carbon, not really. Carbon, not really. If you still remember the trend, the Dominic thing that I told you about. So first, organic chemistry needs bourbon shot. Hooray! All right. Fluorine, oxygen, chlorine. This guy love to have negative charge on it. Hydrogen, carbon down here, not as much. Okay. So what do we mean by that? When there's no significant difference in size, okay, a highly electronegative atom bearing negative charge is more stable. Who's more stable? Look at the look at that EN. Electronegative atom like fluorine love to have negative charge on it. They'll stabilize negative charge better compared to carbon at the bottom down here. So not at all. Which means that fluoride is the most stable conjugate base among all this. Okay, among these conjugate bases, and that means more stable, the strongest acid in this case. Right? If you look at the effect of electronegativity on the stability of the conjugate base or the acidity of the acid, right? So if I set the acidity of methane 1, look at the rest. Ammonia 10 to the 12th, right? So oxygen 10 to the 34th, and fluoride 10 to the 46th. Okay. Electronegativity have even more bigger effect on the stability of conjugate base than the size. Okay, but in this case, because the fluorine is have the highest electronegative atom, right? Oxygen is the second highest there. Okay, all right. If they give you a pKa, if you still remember, so we have a methane 50. That's just an alkane, right? Ammonia 38, water about 15.7, about 16, and hydrofluoric acid 3.1. Really strong acid compared to the other three. All right, now let's say if you get what I mentioned earlier. Okay, so who's the stronger acid? We have H2S and phosphine, yeah, PH3. Okay, well, first thing, draw out the conjugate base. All right, let's see what's the conjugate base look like. Always do that. So I have a negative charge on sulfur and a negative charge on phosphorus. All right, start with the size. Do they have the same size though? If you look at the periodic table, yes, they have a similar size on the same period. So size doesn't matter for these two. Okay, now the next factor is electronegativity. Let's look at electronegativity there. What's the difference there? Well, what we get, sulfur and phosphorus. If you still remember the mnemonic thing, right? Sulfur is right here. Phosphorus is not even in here, somewhere in here. So sulfur is more electronegative than phosphorus. Right? Sulfur is closer to fluorine. Right? So more electronegative than fluorine. Nope, say it wrong. No, sulfur is more electronegative than phosphorus. Right? So which means that sulfur will stabilize the charge better than phosphorus does. So sulfide SH minus will be more stable. Right? More stable, which means that H2S is more acidic than PH3. That's how we do it. Right? All right, so contact checkpoint. All right, I pause the video and try on your own. And now let's check with me. All right. So in A, we have H1 and H2. Who is a stronger acid? If you know the pKa, goes for it. But if you don't know, you can use just those factors I told you. Okay. All right. Write it out the conjugate base. So we have a negative charge on nitrogen and a negative charge on oxygen. So compare between nitrogen and oxygen. First of all, size, not that different, right? But oxygen totally have higher electronegativity than nitrogen, which means OH minus is more stable. That makes OH a stronger acid. Okay, so this proton is more acidic than H1. That's how we do it. All right, now go to B. We have H1 and H2. Well, same thing. Draw a conjugate base first. So I should get this negative charge on nitrogen and negative charge on sulfur. Okay. All right. Start with the size first. Do they have different in size? Oh, way different. Sulfur is period 3. If you look at the periodic table, nitrogen on second period, right? So sulfur is much bigger than nitrogen. Bigger, the charge will be happier, like spread out in a larger area. So sulfide S minus is more stable, and that make the H2 is a stronger acid. Okay. All right, now let's go to the next factor.